So I was going to leave threads, but I promised a girl a Python programming video. So let's just launch Jupyter Notebook here. You could use an IDE or something like a PyCharm, but I've been using this more and more. Okay, let's see here. New Python 3 notebook. And we will call this primes, I guess. All right. Now, if you want to factor a number, that can be an expensive operation. So I just want to show you here. We'll have a function called naive factor that takes a number n. And then if n is, I don't know, less than 2, then we will just return the number. I guess return an array of the number. We're not going to deal with negatives. If 1 or 0 gets passed in, just whatever. Otherwise, we're going to go through and we're going to look for potential factors. So we'll say return value is a list, and then for I in range 2 to n plus 1. What are we going to say? If I is greater than n, then we're going to break. If n mod I equals 0, then that means it's wait. While n mod I equals 0. Then we're going to divide n by I, and we're going to append I to the list of factors, right? So that makes sense. Let's see here. Just return ret. And we can test our function very simply by just saying print naive factor, I don't know, some number. Well, let's start with a prime. 5, right? Then obviously the only prime factor of prime would be itself. We do a composite number. 2 times 3 is 6. Do, a bunch of 2's multiplied by themselves. Okay, it works. The problem is that it's very slow. So let's see if we could time this. So for I in range, I don't know, just 5,000 or something. If we called naive factor every single time with the number, eventually this is going to start taking a while. Let's time it actually. Let's say start equals time.time. Need to import that, I guess. And then we could say end time equals time.time, and then print, what are we going to say? I guess elapsed time is end time minus start time, right? And then we could see. Well, let's start with something smaller, like 100. Okay. So that's not that bad. It takes 0.0001 seconds. But if this number starts getting bigger, it will start slowing down. 0.4 seconds. This is starting to be like, actual time here. So, oh boy. Oh boy. Well, now I've kind of done it. Might have to interrupt it now. Ooh, what have I done? Well, I can talk while that's running. So, there was this Greek guy named Eratosthenes, and he came up with a technique for finding prime numbers, and that could be useful for our purposes. Okay, so let's just make a note here. 10,000 took, I'll just round, 34.8, no, 34.8 seconds with naive factor. That is slow. That is definitely slow. So let's not do that anymore. So let's try to find prime numbers. Now, we could start off, prime number is just something that is only divisible by 1 or by itself. So we could say naive is prime. Well, I'm repeating myself at this point. Let's just jump right into the sieve here. So let's say we're going to have a list of primes and then a prime set. So this will, it'll be able to instantaneously find things, whereas primes will just be, indexed for going through in order. So this is going to be like 2, 3, 2, 3, 5, 7, etc. So yeah. So we're going to say max number equals, how big do we want to make our sieve? Let's start off actually kind of small. Let's just say 1,000. Now, the way that the sieve works is that you will mark things incrementally. So you'll start off and it'll have all of the numbers, like this. And then the first one in your list is going to be a prime number. And so you know that that's prime. You're going to set that one aside. But then you know that every multiple of it is not prime. So the 4 can be gotten rid of. The 6 can be gotten rid of. The 8 can be gotten rid of. The 10 can be gotten rid of. And then you have less numbers. So then 3. 3 is prime, but 3 times 3 is not prime. So yeah, that makes sense. I think that makes sense. Okay, so now 0 and 1 are special cases. They are not prime numbers that don't really enter the conversation. So we're going to start off by just defining them as not prime. And then we will start off everything else, and we don't care if we go 1 over. That's fine. Fine with me. Okay, so the way that we're going to execute the sieve is we are going to say for I in range length of primes. You know what? I have primes and primes. I should call this sieve. Length of sieve. Okay, now we're only interested in doing something if we encounter a true value. You know what? I'm going to set this even shorter so that we can print it at the beginning. Okay, so look. If sieve of I is true, then we're going to do something with it. So what are we going to do? We're going to just print it, but then we have to mark all of the multiples as not prime. So we'll just use a second for loop. For j in range. And where do we want to start? We want to start, I guess, I times I, because that's the lowest number that could be a multiple that wouldn't already have another factor. And then it's going to go through length of sieve, and it's going to have a step of I. So it's going to jump. So 2 is going to go to 4, and then it'll go, 4, 6, 8, 10, all the way to the end. And what do we want to do with that? Well, we just want to set them equal to false so that we know that they are not primes. And this, if we run this, should give us the primes up to 100. Might give us 101 too because we went 1 over here. We'll see. Yeah, 2, 3, 5, 7, 11, 13. It looks good to me. All right. So instead of printing these, let's add them to our list of primes here. Primes.append I, and then prime set.add I, like that. get down here, that should give us, just a list of the primes. And then the prime set should be the same thing, just in set form. So 2, 3, 5, 7 looks good to me. Now, with a list of primes, we should be able to make a much, much better factorization method here. So let's start off with our naive wait, indent is not good there. Okay. Normally I'd call it factor, but I don't mind being verbose right now. Factor with sieve. And same thing, if it's less than 2, then we're just not concerned about it. But now, instead of saying for I in range 2 to n plus 1, we're just going to say for I in primes. So it's almost the same algorithm. It's just, there's just not a bunch of composite numbers that we're wasting our time on. And this should be much faster. If we copy this down to here, and then instead of doing, so let's see. So this took 34.8 seconds with the naive factor. Let's see how fast it goes here. 0.116 seconds. That seems much, much better, which is kind of what we were going for. But we want to make sure that we didn't mess anything up. So let's go 1 to, 1,000. And then we will check that the factor with sieve matches our expectation of the naive factor. And I mean, it should, but we'll just run that. And oh boy. Oh dear. Oh my goodness. Well, I guess this is why we check. What is the assertion? Okay, factor sieve. Doesn't matter if it's going fast if it's giving us the wrong answer, right? And then naive factor. I am legitimately curious. I was expecting this to just work. So let's see what it's angry about. List object is not callable. Okay, that is not what I was expecting. Just need to learn basic syntax, I guess. Whoopsie. All right, 0 and 103. Very, very odd. Oh, I made a mistake. Okay, first thing we need to do. This only goes as far as we have defined it, right? Yeah, exactly. So n has to be strictly less than or equal to, let me think, well, it would be the greatest prime squared. So as long as it's lesser than or equal to that, then we should be able to calculate it. And then at the end, if if n is greater than 1, then whatever is left over is also a prime. So we say ret.append n. And now our test should pass. That is the importance of testing. All right, and it did not take very long. Let's do a few larger ones. Oh, how can I get some random numbers here? Now, naive factor should be fine for like a single integer. Let's do import secrets, and then we can do secrets.rand below 1 million. Okay, there's a number. But we're not going to be able to go this high unless we increase this max number here, because this factor with Sieve is only going to work if our largest prime is large enough to accommodate the largest possible number that we could throw at it, which means whatever this number is, it has to be at least the square root of that number. And, well, I have a calculator right here. What is the square root of that? Ah, stop. I just wanted to get rid of the carriage return. Yeah. So, yeah, as long as max num was, 926 or greater, we should be fine. Which it is. 1,000, excuse me. And you should be able to go like all the way up to like 10 million or something, no problem. So we run this, no assertion, it works. Everything's good. I'm satisfied. So, hope that was fun. And now you know how to do a sieve of Eratosthenes. And I don't know how to stop the recording. Here we go.